So this is the kind of the fourth part D of our transport aircraft electrical systems, and we're going to be looking at AC generation and load shedding. We covered DC generation when we did DC, just because it's a pretty basic thing, a transformer rectifier, being solid state and all that. There's not a ton to it. If you go into avionics or electrical and you want to work on those kind of things specifically, you'll get a lot more on that. But if you're doing like line maintenance, engine maintenance, that kind of thing, you're going to be dealing with the AC generators that are mounted to the engines, as well as some of the airframe, emergency backups and alternate sources and that kind of thing. So AC generation, I talked about it, different sources. Our primary source, the one the aircraft is going to look for and is going to draw power off of if it's available, is going to be our engine-driven generators, right? The aircraft is designed to be self-sustaining. The term I heard in a video I was watching recently is they called it a closed envelope, right? So once the airplane pulls away from the gate, it's its own thing. Everything to support the aircraft is on board the aircraft, or once it's unhooked from ground power and whatnot. So the engine generators are going to be the main item there. There are going to be auxiliary sources, though. The APU generator is an auxiliary source, okay? And that is if the engine-driven generators aren't available, the engines either haven't been started yet or you shut the engines down. If the APU is running and the generator is available, most of your modern aircraft now are going to automatically switch. That logic in the electrical control systems will automatically swap it over to the APU generator. Older aircraft, you had to do that manually. You had to disconnect them. You had to connect the APU generators, disconnect the main generators. But everything now, it's, most of those controls, when you're looking at controls in the earlier lecture, had an auto position. And so that auto position means this logic all kind of takes place automatically. We'll also have hydraulic driven generators. So these are where we can take power from our hydraulic system, and on transport aircraft, when we get to hydraulics, we'll look at it. Your hydraulics typically are driven. Each hydraulic system typically has a pump driven directly off of an engine, and then a pump driven by the electrical system. And so that pump driven by an engine, if you lose an electrical system and need to get it back online, the hydraulic pump being driven by the engine can supply hydraulic pressure. That hydraulic pressure can drive the hydraulic driven generator to bring electrical, to have an electrical source. And then we have emergency sources. Now, the auxiliary sources often will be used in an emergency if they're available, right? The APU generator in particular tends to have a lot more load rating, or a lot higher load rating than anything else listed here below it. Okay, so the main generators are going to have the main, the highest load rating. They're going to be able to handle everything. APU generators, depending on the aircraft, some aircraft, smaller aircraft, the APU generator can handle anything. Larger aircraft, they may not be able to handle quite everything, but they're definitely going to be able to handle more than these hydraulic or these different emergency sources. So if we can get the APU going and have that, that's going to be preferred over a purely emergency source. And then these emergency sources, air-driven generators and battery with inverters, really their purpose is there in a situation where the engine stopped working altogether and the APU is not available. So the plane becomes a glider, and it could be fuel exhaustion, could be a double bird ingestion. Anyone know what today's the anniversary of? By the way, saw it this morning. What's that? The Miracle on the Hudson, the A320. I think it was a 320, 319, 320. That landed on the Hudson River. I think it was about 12 years ago. So that was on takeoff. They went through a flock of birds that took out both engines. That airplane would have been on emergency power. I believe that has an air-driven generator, if I remember correctly, during its descent before landing on the Hudson River, or gliding to land on the Hudson River. So that's that kind of a situation, because they may have been able to get the APU generator on, but I don't think they had quite enough time to. I don't remember I'd have to go look at the report. Last one here is ground power. The last thing the airplane's going to look for is ground power. Why is emergency above ground power? Why is this? We use it a lot more often. but you can't use it in the air. So you want the plane to prioritize emergency power. We don't want it looking for ground power when it's a glider in the air.
Just hook up a GPU.
And yeah, we can't hook up a GPU in flight, and so we don't want it looking for ground power if we're in the air. Now there are safeties in place because we don't want the air-driven generator to deploy in the air or on the ground, excuse me. But you know, it is going to look for those emergency sources before ground power, particularly in a flight condition. So here we have a integrated drive generator, also known as an IDG. Some of you, most of you, have looked for one of these already. Where did we find an IDG yesterday, those of you that had lab? The JT9, the big 747 engine that's in Hangar 1. So this is made up of two parts. Now, the one you'll look at on the JT9 is going to be a little bit different than what I have pictured here. So this is made up of two parts. We have our constant speed drive. There's where the drive portion comes from. And then a three-phase 120 volt, 400 hertz generator, right? And these are mounted to the accessory gearbox. You can see in this picture, this end right here, we've got a spline shaft on the left side. This is where this flange is what connects it to the accessory gearbox. And you'll have a accessory gear that ties in to rotate that flanged input shaft. And so here is the constant speed drive on the left. Okay, and you can kind of see there's a seam right here. There's like a seal with bolts, right? Bolting what looks like two kind of halves together. So our constant speed drive is this part here with the input shaft. And now inside of here is eventually an output shaft or an output connection to the generator, which is this back half of it, or this in the picture, the right-hand path. So here, this configuration is probably the more typical configuration where you have the constant speed drive and the generator piggybacked on one another. In fact, when we would work with these on the aircraft, the airlines, that kind of thing, we never changed just one or the other. They were always changed as a unit because this CSD, constant speed drive, and generator we didn't separate those. Those would be separated at like an overhaul shop or a back shop. It's very rare that a mechanic or a technician working on the aircraft directly is going to separate these. Now, those of you that looked at the JT9, what was different? It's different. They're separate. For space and weight and balance configurations on the JT9, they do separate these. They are two separate units. The constant speed drive is on the back of the accessory gearbox. So the accessory gearbox drives that. And then if you were to take those off, there's a shaft that runs back through the accessory gearbox to the front side of the accessory gearbox where the generator is located. But effectively, they work exactly the same. It's just they're physically separate. So what I mean by that is if we have our nice, good marker, you can't see that at all, can you? No. Here's our accessory gearbox hanging down off the bottom of our engine. Our engine's up here, okay? And so we have our constant speed drive attached here. Our generator is attached here. The accessory gears are driving an input shaft to the constant speed drive. And then there's another piece going through that connects the constant speed drive to the generator, okay? Normally, you're going to see this configuration on the board, which is piggybacked. Okay, that's a lot more common. Again, I think this was weight and balance, size, making it fit within the cowling, that kind of thing. So if we look at more of a pictorial view, what the different things are, you can see that same division point between the generator component and the constant speed drive component here. And then a few of the other features on here. So one thing to notice, what do you see a bunch of things on the drive side that it's dealing with? Oil, lots and lots of oil stuff. So the drive is oil filled. In fact, it uses oil in order to couple the two sides. It is a hydrostatic transmission. So some of you may be familiar with those if you've worked on like equipment or ATVs, side-by-sides. Those all use that hydrostatic type drive.
Lawnmowers.
Somewhat zero turn and farm or lawn tractors, a lot of those use hydrostatic drives. So it is oil filled, okay? It's a separate oil system from the engine. It's not sharing oil with the engine. It's got its own little oil system. And so in there you have a fill port, you have a oil filter. Here's a sight glass so you can see. And a lot of these have two sight glasses, one on the left, one on the right. Why would they have two? Depends on which engine it's installed on or which side of the aircraft, because a lot of times the engines are slightly rotated one way or the other, so the oil is going to be a different, or it'll have two different full marks on it. It'll have a full mark if it's mounted on a left engine. It'll have a different full mark if it's on the right engine, because they're slightly different tilts from side to side. Okay. You're going to have, so the oil sight glass, DPI indicator or differential pressure. There's going to be a little red pin that can pop out here if your filter starts to get clogged. And then what's not shown here, they show the oil, they show oil out port. There's also going to be a return port. That is going to travel to some kind of an oil cooler, right? This thing's running constantly during flight. Oil's going to heat up, and so there's going to be an oil cooler. And most of those oil coolers they're going to be located somewhere on the engine, and they almost always use fan bypass air. They take the cold air that the fan is accelerating on the engine and run it across an oil to air heat exchanger to cool the oil. Okay, so they're, again, self-contained. They don't share oil with the engine. They do typically use the same oil as the engine, though, like the same type of oil. So they use turbine engine oil. And that way you don't have to stock turbine engine oil, and then you would have to stock, IDG oil, and then like the starter also has oil. You wouldn't have to stock starter oil, right? Though typically all the accessories on the same engine, if they use their own oil system, they're going to use the same oil that is the engine that they're on, so that you really only have to have one type of oil to service everything on that engine. Yeah. How do you change the oil? They're going to have you see this overflow drain plug here? So you can remove it's like two parts. You remove the lower part. That's like an overflow standpipe for filling it. And then if you remove the upper part, it's a whole plug and it'll drain out. And then this right here is a filling port. Typically you have a little cart that's got a hand pump on it, and it hooks to that with a quick release fitting. And so the way you service them is you remove the overflow plug, right? So inside of one of these, if we look at the oil sump, you've got, here's your overflow port, and then you fill oil in, and you fill the oil, you remove the plug from this, and you fill the oil. When it gets to that point, it starts to leak out that standpipe. And if you look at the sight glass, that'll be at the full mark on your sight glass. So they're pretty, as long as you don't leave that plug in while you're servicing it, they're pretty dummy proofed. I've seen them. They also have a vent on them, by the way. So there's an air vent. What does that mean? Well, if you don't remove the plug from the standpipe, you can still fill it because the air can escape. So then you can fill it all the way up. So I have seen them overfilled before, where somebody they forgot to pull the plug from the standpipe before they started pumping oil in.
Have you seen it where oil from the engine actually got into it?
It really can't. It can kind of get between, but it can't really get into the oil system.
So it can't like leak past the seal or anything like
that? If it leaks past the seal, it's a very small amount. It's not enough to affect the level in there necessarily.
So you won't even notice it?
Not really. There's where these connect. Let me go back. Where these connect to the gearbox here. And on the other side, so you have a seal right here at the shaft. And the part that this keys into also has a seal on it, right, to keep oil in the engine. There's a gap in here, an air gap, and there's actually on the engine, there's a little drain on the bottom of it. So if oil leaks past this seal or this seal into this what's called gallery or cavity, it'll drain through that, and there's a drain on the bottom of the engine. There's a whole bunch of tubes that all run to the bottom of the engine. It's called a gang drain. They all gang together, and you'll get oil dripping out of that.
So it looks like, you'll see it on the ground essentially.
Yeah, you'll see it dripping out of the gang drain.
All right.
Okay. So, nope. Well, you'll see oil dripping out of the gang drain. Then you got to figure out: is it the starter? Is it the IDG? Is it the hydraulic pump? Right. And there's ways to figure it out. A lot of them you can kind of tell which tube it's coming out of, and then You know, if it's the one going up to the hydraulic pump and it's oil, it's coming from the engine seal. If it's hydraulic fluid, it's coming from the hydraulic pump seal. But the problem is that hydraulic pump seal went bad. Now you're probably gonna have to replace the engine oil seal there too as well.
Because
I gotta move on. So the IDG, remember, we've got a variable input speed based on our engine, right, going faster and slower. And we need to keep that output speed constant so that our frequency of our generator remains constant, 400 hertz. And it does that, as I mentioned, with a hydromechanical system. Sometimes you also have things like axial gear differentials. There's going to be some type of a governor system. Have you had props yet? Props? No. Did you talk about prop governors? You have others? So I think with the new curriculum, you may not have had it. Okay, if I put my hands like this and I go like this, do you? There we go, flyweights. Okay, so the governor in these are flyweight based, and it's going to control that output speed based on, if it's in an overspeed condition, it's going to slow down the output. So the flyweights are connected to the output side. So if the output's turning a little bit too fast because the engine's sped up, the flyweights are going to go out. That's going to it's going to port fluid in the hydrostatic system to slow the output down until it gets back to that on-speed condition. If the engine slows down, the output starts to slow, those flyweights are going to come in. That's going to port fluid the other direction to speed up the output to bring it back to an on-speed condition. So it uses a similar type of governor as what you would see in a propeller. By the way, engine hydromechanical fuel controls, they do the same thing on a turbine engine as on as the prop governor on a piston engine. So the way a hydromechanical transmission works is you essentially have a hydraulic pump and motor assembly where the pump is driven by the input shaft from the engine, and that's going to pump fluid. And then we can adjust how much fluid that pump is sending out to a hydraulic motor, which is driving the output to the generator. Okay. And if we reduce the amount of fluid, at a given RPM, at a given input RPM, if we increase the fluid flow, that's going to increase the output RPM. If we decrease the fluid flow, that's going to decrease the output RPM. Or consequently, if the RPM going in increases, we can drop the fluid flow, the volume of fluid, and that's going to slow down the output. Or if the RPM decreases, we can increase the amount of fluid being pumped with each rotation, and that's going to increase the output RPM. So we change the flow rate to kind of in an inverse fashion to the RPM to keep the output stable. Okay, and it's doing that with oil and flyweights, doing that. So I've got a video here, and so we can see how one of these things operates. One other item that these are going to have is that that gearbox is going to include a system for automatic and manual disconnect. And so in case of a problem with the generator, say it gets bound up, your windings come apart, something binds in there, we don't, or there's just drag being occurred with too high of a load or some kind of an issue with the generator controller that causes a load issue. What's more important, electricity or thrust? Thrust is our most important. So we don't want to drag the engine down. So we have the ability to press a button, or in a lot of cases it's automatic, where there is a physical disconnect built into the constant speed drive that will physically separate the input shaft from everything else in there. And that's what's shown here. So on our drive, here is the input shaft, the spline part. And it has kind of a sawtooth keyed coupling. Now this is showing it separated, disconnected right now. Here's where it goes to the rest of the constant speed drive. So if anything goes wrong, there's this pin. It's normally held down. Okay, when it's held down, these are able to be held together. They come together. But if this is spinning and this little keyed part, this is threaded right here, like a screw. And if this disconnect plunger comes up and hits it, that rotation, it's going to thread itself against the disconnect plunger and pull away from the input shaft side. And so now you've physically connected. So this part right here will continue to spin with the engine. you can see there's not much there that can bind up the engine. And we've disconnected any hydromechanical unit, any reducing gears, and then the generator that's downstream by separating those. Okay. There's the way it is done is through a solenoid. So there's a electrical solenoid that can be activated either by, there's a button for all of these. There's going to be a button in the flight deck that allows the crew to activate it manually. Or a lot of times the generator control unit has the ability to trigger this as well in case it senses. That's the little computer that controls the output and the generator. The generator control unit is able to trigger this if it senses a generator problem as well to prevent engine damage. In addition to that, any device, and this is when you have your turbines class, we'll talk, you'll kind of look at these, but any device attached to the accessory gearbox, you can see that this shaft has a very skinny section right here. Anyone know what that's for? That's a shear point. So that is, if this actually does get locked up, that is weak enough that it can shear and break. Just a word of note from the maintenance standpoint, when you're installing and removing these kind of things, starters, generators, hydraulic pumps, anything that goes in the accessory gearbox, these things are heavy. I mean, the regional jets, these integrated drive generators, they weigh somewhere between about 60 and 80 pounds. On a large aircraft, they can weigh over 200 to 300 pounds. So when you're installing and removing these, you got to be real careful that you don't let them kind of tip. They have to be supported, because if you allow the back end of them to tip when they're not actually clamped and held in place, bolted in place, it can crack that shear shaft. It can put a load on it and crack it. So you just have to be aware of that during maintenance. So we talked about hydraulic oil and the provisions for cooling. So here's our IDG, kind of just how it, it'll be installed. There's those two, the oil lines, the output and the return, going to like a heat exchanger, air-cooled oil cooler in this case, which the air source is fan bypass air that's going to get blown across there. Not to mention when we're flying at altitude, it's really cold, but even at ground level on a hot day, these have to provide enough cooling so that fast moving air across it is going to be able to do that. So most of them are air oil coolers. There are some aircraft that use a fuel oil cooler. And so that is, you take cold fuel, a liquid to liquid heat exchanger, and you use cold fuel to pull it away. It also, the positive, what's the additional benefit of that? It warms the fuel in case there's ice crystals in it. It helps to get rid of ice crystals. However, most of these are air cooled. Usually where you see the fuel oil cooler would be for the engine oil cooling. Okay, we use fuel to cool the engine oil rather than the IDG oil. If we look in the back part, it's a 3-phase generator, right? We got to create AC, and it's those 3 different phases. Remember, is how we refer to the phases. Talked about it on, what's that? Well, there's 3 sine waves, right? 3 phases. What do we refer to them as? If you're trying to talk about one, the other, or the next one. A, B, and C, right? So phase A, phase B, phase C.
I'm blacked out.
But you can see there are a whole bunch of commutators and exciters and magnets in here. So here's kind of just showing that. So there's the engine with variable RPM to our constant speed drive, putting out a constant RPM. And now we look inside of here and you got all kinds of things going on. Now, the one thing I don't like about this diagram is it shows everything the same size. Okay. This first one here is going to be really small. Okay. This permanent, it's called permanent magnet generator. You have a permanent magnet. That's exciting these coils. That's just putting a little bit of voltage. That's what runs the generator control unit. So the generator control, 2 reasons. One is the generator control unit needs power to bring the generator online before the generator's online, right? So if it ran off the electrical system, I guess it could run off the DC, like the batteries or something.
Generator has to make power to make the generator.
Exactly. So, okay. The other reason is if we lose our electrical system in flight, this is self-powered. So if the engine's running, it's going to be powering the generator control unit with the idea that hopefully we can get the generator back online. Okay.
these stator coils, I just want to make sure they're not attached to the actual output shaft.
These, right, correct. Yeah, stator means stationary.
Yeah.
So they're stationary. This magnet right here is spinning, and that's going to create, and it is AC. I can't remember. It's like 36 volts. It's not a great picture. 30 volts. You know, it's enough to run this little box. I mean, this box is literally the size of my fist. It's a very small controller. There's not a lot to it.
Probably held together by 1/4 screws or something.
I don't remember. I never took one apart. So that's going to power the generator control unit. And that generator control unit then is what's going to regulate the rest of this. And the way it's going to regulate the rest of it is through this, you know, voltage regulator right here. And so the voltage regulator sends power to this exciter, stator. Okay. So this is basically an electromagnet. So you have a stator and a rotor that's AC armature. That produces a small amount of AC that we then bring into a rectifier coil. So this is another electromagnet. And that is the electromagnet that works with the main, that's that, and it's a rotating, those three phases are hitting different points on it. So this is creating an AC signal that's then powering the main generator stator. So you have a big stationary coils at the end where the actual power being sent out to the aircraft is going to be generated. And that's what these three outputs to GLC, this is going to the aircraft. Okay. That exciter rotor is rotating. Yep. And that's rotating in the field produced by this stator, this DC stator. So these two, so these first two are a pair, stationary, rotating. These are a pair, stationary, rotating. And then these are a pair, now it flips, it's rotating and stationary. Okay. And that's where your output is, you know, where you're getting your output. Okay. And so that's where, you know, this, everything to the right here, you know, is not going to turn on unless this sends a signal to this exciter stator DC to basically power everything else up. And it's also going to control the voltage based on the strength of this field, which affects the strength of this field, you know, that it just cascades down the line to control voltage. Okay, it controls the strength of the magnetic field in this exciter, this DC starter, exciter stator, and that's what controls the voltage through the rest of the generator. Okay. Unless you're doing generator overhauls and testing, you're probably never going to into it this deep, but it gives you an idea of, we just need to understand that these are, it's an electromagnetic generator that is controlled by our generator control unit through multiple sets of coils and electromagnets. So here's looking at kind of the control panel side of it. So if we have a fault with our IDG, oftentimes we have a fault light, but there's that disconnect. That's what triggers that little thing to shoot in and separate. That's that physical disconnect. Okay, we have a switch to turn power on and off. Okay. Oh, I did miss one thing here. One other part here is we do have the ability to reset. So when the engine's not running, you can pull this ring right here and pop it back down. Okay, so they can be reset after they've been triggered. We would test them in maintenance. We would actually press it and make sure it trips the generator offline, disconnects. Now, if they do that in flight, they have to record how long it ran, how long the engine ran with that disconnected, because ours could run like 10 hours before, if it ran collective more than 10 hours, we'd have to keep track of it. It happened more than once. They would have to change the generator out, because essentially that first part of the generator was running without any kind of lubrication when it's disconnected, right? Because, you know, that right part there would still be spinning. The oil pump is connected to this piece over here. And so this little piece right here could run for 10 hours before you would have to change the generator if there was no oil flow. So we have a generator power off reset. This is what sends the signal. That switch is what sends the signal to this, telling it you want power, right? Now that's mostly automatically controlled nowadays, where if the engine RPM is high enough, the generator will automatically come online. I do have a video here that I put in for you guys to watch on your own. It's a little bit longer, but if you want to see how the A320 generator, which is a good example, is constructed and then operated and serviced, it's a pretty decent video about that. Okay. But now we're going to move on to variable frequency AC. So these are similar to our IDG in terms of the generator being similar, but a variable frequency AC generator doesn't have a constant speed drive. And so this is some of your newer aircraft have gone to, I mentioned it in the first kind of discussion we had, have gone to variable frequency. And it eliminates that heavy constant speed drive in order and basically puts the rectification, the frequency adjustment on the individual components that need it. Because again, a lot of those components that just heat up, they don't care what the frequency is. So, heated leading edges in the 787, you can run wild frequency through them, they're still going to heat up no matter what the frequency. But they'll still have some kind of a disconnect on them. They'll still have a physical disconnect, okay? Some of them have the ability to operate as a starter. Your normal IDGs are not going to be used for starting. You're going to have a separate starter. But like the 787, the constant or the variable frequency generators are actually a starter generator. You can send power into them in order. They are an AC starter. So the way they work is you have a battery, powers an inverter that then sends power into those starter generators to get the engine spinning. Some of them are 115 or 120 volt, 787, a few are 235 volt, that higher voltage. But that wild frequency is directly affected by our engine RPM. Okay. APU generators work same way. They have probably more in common with those wild frequency generators than anything. But they're going to put out a constant three-phase 120 volt, 400 hertz. But they don't have a constant speed drive. Why don't they need a constant speed drive? The APU runs at a constant speed. APUs come on, they go up to 100%, and they want to stay there. If a load's put on them, they add more fuel to maintain that speed. So many are rated to the same current rating or same load rating as the main generators, especially in smaller aircraft. But some of your larger aircraft, they just physically are not big enough to handle power for the entire aircraft. And we talked about frequency controlled by the APU. Hydraulic driven generators, similar phase, three-phase 120 volt. These have a hydraulic motor coupled with a small generator. It's kind of like that in that constant speed drive. You had the motor on the output side, right? It's basically that. So instead of using a CSD to drive that motor, you use hydraulic pressure from your hydraulic system. These are limited capacity. They're used if you're down to, they are kind of a auxiliary emergency source. And so, they'll be used in a case where that is, and they're limited in what they can provide. I'm going to save emergency sources for later. So we're going to stop there.